Now, Simon, I'm pretty sure that when you talk about the VFD, right? Is there a VFD that can help pumps run less stress, cooler, quieter? And do you have any data to show it?
Yes, absolutely. So let's go through data to back up what we say we can do. We've been through external testing with third-party lab to test our Clean Power VFD and see how it can output 3 sine wave signals directly to the pump. With very low harmonics, virtually no common mode voltage, and low common mode peak. The external lab setup has a transformer that goes and does a very stiff grid. It has a drive system under test with about 500 feet of cable, so we do have long cables in there, and then we have the motor. In terms of drive system under test, we have tested the Clean Power VFD, a conventional 6-pulse VFD, as well as a conventional 6-pulse VFD with both passive harmonic filter and a sine wave filter on the motor side. So the first thing you can see is that there's a clear difference in the signal going to the motor. Just visually, you can see how the motor VFD voltage and VFD current are significantly different with the conventional 6-pulse VFD. You're not having that square signal that you talked about that is generated by the PWM. So even before we're doing further testing, we can assume that a lot of the PWM damage you talked about would be mitigated. Same thing for the common mode voltage, where you can see that it is much smaller amplitude. And even then, when we compare between the left side of the screen with the right side of the screen, we're also seeing that even though the filters are helping quite a lot, we're still seeing a much nicer signal, for example, on the VFD voltage. But let's dig a little bit more in those data and those results. So in terms of common mode current, not surprisingly, both on the current and the current peak, it is the conventional VFD that has the worst performance, that pink line at the top of the graph. And we're seeing that if we're adding the sine wave filter, we are helping the result. So we are decreasing both the common mode current and the common mode current peaks. But it's really the Clean Power VFD that's outperforming everything here, with virtually no common mode current getting through with the very, very low value. So this is something where the Clean Power VFD can offer benefits that, yes, is somewhat mitigated by filters, but not completely. Now, continuing, common mode is one of the villains you talked about, Bobby, but the other one is the motor peak voltage, and which is made worse as we get longer and longer cables. And in this case, with 500 feet of cable, you can see that the conventional VFD definitely is above a 1,000-volt limit that we find in many cables. Actually, we can even ask ourselves how the motor and cable can withstand this for very long when you're reaching close to 1,800 volt in peak voltage. In this case, we can see that the sine wave filter is doing its job, really maintaining a very constant peak voltage at the motor terminals. And the Clean Power VFD is doing the same, having a very flat performance. So this is what we want to see. You could ask about, hey, there's a small difference between the Clean Power VFD and the sine wave filter. Indeed, the Clean Power VFD has an active front end, so is able to compensate voltage drop. And so this is why you're seeing that voltage a little bit higher. Actually, the active front end from the Clean Power VFD is capable of compensating that voltage drop up to 20%. So giving the opportunity to have even longer cable without any issues. Now, taking a sneak peek on the line side, actually, we can see that the line side is also displaying quite nice voltage and current waveform that you can see at the top. And you can compare that to the conventional VFD with the disturbed current and voltage from the harmonic. Here again, you can see that the passive harmonic filter is actually doing its job, and we are having much more comparable results between the top graph and the bottom graph. On the right side, we're seeing the impact of the Clean Power VFD on the power factor. So certainly the pink line with the standard VFD, we are seeing better power factor at about 94 or 95, but it's not unity power factor as you're seeing with the green line at the top with the Clean Power VFD, really maintaining unity power factor from a motor load of about 65%. And the harmonic filter here is actually having a inverse impact where the power factor is actually decreasing as your motor load is going up. Now, going back to the motor, you talked also about the impact of temperature on the motor lifetime. So here, it's interesting that because we're supplying with a sine wave the motor, at every speed load combination, you're seeing an about 10% impact on the motor temperature, where the motor temperature is much lower with the sine wave than with the square signal. And knowing, and I think you mentioned it, that every 10 degrees Celsius temperature rise has a 2x impact on the lifetime of the motor. So really decreasing in half the motor life expectancy. This 10% difference, which is about 7 degrees Celsius, has a significant impact on the potential lifetime of the motor or your pump that you're running with your VFD. And finally, to conclude our test results, we can see that the harmonic situation on the line side is also quite similar between the passive filter and the Clean Power VFD versus the standard or conventional VFD that really has around 30% harmonic on the line side. And so in both with the SmartD VFD and the passive harmonic filter, we're meeting IEEE 519 standards, maintaining below 5% the harmonic, even in a very stiff grid environment. And same thing for the voltage total harmonic distortion, where we can see that the Clean Power VFD actually even outperforms the passive filter performance.